This is the oral presentation for Electronics 2 for the lab portion. Our group includes me, Daniel Miles, and Ben Morse, and Mohammed Hussein. Although for this oral presentation, Mohammed Hussein will not be part of it because he had a scheduling issue. He'll be doing his own individual oral presentation and turning it in by himself. The lab we chose to present for oral presentation is Lab 3, which is the design of a multi-purpose MOSFET amplifier. Okay, the objectives for this lab, or this is the outline of the objectives for this lab, which include the lab objectives, oddly enough, circuit analysis, CAD simulations. There was no experimental for this lab in particular. Then we have the discussion, which will be a table comparing all of the data compiled on the BJT amplifier, this amplifier, which is only simulation, and the LM741. That'll be the conclusions at the end, which will just be summing it all up. Okay, our lab objectives for this one was to simulate and design a two-stage transistor level operational amplifier using only MOSFET transistors. Use the op-amp design to create an inverting amplifier with negative feedback and a given gain. We'll see that later when I show you the diagram. And then we're supposed to compare it in the table like I mentioned before. Here is the diagram of our circuit that we used. As you can see here, here's the differential amplifier with the only MOSFET transistors. You see all transistors in this thing were only MOSFET. Here we have the inverting input, and it's connected to a negative feedback from the output. And the gain we're looking to get here is 5 based on the 2K and the 5K. And here's a current mirror, stage 1, stage 2. Here's all the theoretical analysis going into this. Can't really go more in depth in this. This was actually Mohammed's part of our lab, so he will probably explain this a lot better in his own video. Okay, here's the DC bias point analysis, which was the first step they asked us to do. Here, the relevant things we're looking at is that at each gate, the current for each one of the 4 gates in the middle of the differential amplifier have a 0.5 milliamps. As you can see here, 0.499 is pretty close, so I'm just going to call that a win. Also in the 6th and 7th, if we go back to the diagram, if we go back to 6 and 7, we're down here. These ones should have about a -1. And if you go back again, you can see here where we took the gate sources on 7, we got a -1, source, -1. And then if you look at 7 or 6, got a -1. So, okay, here's just transient analysis. This is just showing that when we ran that circuit we saw before, that it'll give us our gain of 5, which you can see here, 100 millivolts, and it goes up to 5 millivolts. That's a gain of 5, and you can also see that it is in fact, inverting by the way the waveforms go. And here, our AC analysis for frequency response. This is necessary to find the unity gain bandwidth frequency, which in this case can be found by -46 if you go down 3 dB, gets you about -49. When we did a cursor, which is not on here, but we did find precise sets, it comes out to about 1.1 megahertz for our unity bandwidth frequency. And then for this one, it is a temperature stability analysis. This was just showing how the circuit reacts when you increase the temperature. And as you can see here, this is extremely focused in. We're at, difference between milliseconds, like parts of milliseconds, and it's only like moving by 0.001 millivolts. So that should tell you that voltage stays pretty stable even with temperature changes. And then from this point on, it's going to be Ben explaining the rest.
All right. So in this graph, we showed the output voltage versus load resistance, which basically is showing that as the load resistance is varied, it makes absolutely no change to the output. So this is the distortion analysis and maximum output swing, and this shows that as we sweep the input going from 0.5 to 3, that the output will clip as it gets larger input. So for this section, to find the common mode rejection ratio, we had to find the common mode gain and the open loop gain. The common mode gain was found by tying the inputs together and getting the output, and the open loop gain was found by putting a voltage into the non-inverting input and tying the inverting input to ground. And then we put it through this equation here to get 200. For the power supply rejection ratio, we changed the values of the power supply going from 7.5 to 15, and it showed basically no difference. This actually is supposed to have two lines, and as you can see, we're zoomed in so far that the change is 17 microvolts, and we swept it even further, going from 7.5 to about 100, and it still had no difference, meaning that the power supply rejection ratio is pretty much zero. For this one, we took the input bias currents, which was tying both inputs to ground and reading the current going into each of the gates. And as you can see, we're in femtoamps, so both of them are essentially zero. For slew rate, we did a voltage follower and assigned a pulse of one millivolt, and to get the time that it takes to go, we took from 10% to 90% and found that to be 0.05 volts per microsecond. There was no experimental portion of this lab, so and then for this, we show the comparison between the BJT circuit, the MOSFET circuit, and a LM741 off-the-shelf op-amp. And as you can see here, the input impedance is very high, and the offset is very low, but that's mostly because it's a simulation, and if this was actually built, it would perform more reasonably. So in the simulations, everything was pretty close to ideal, as the MOSFETs performed pretty much perfectly. We ran into some issues with the BJT amplifier, so this previous table here, it should be taken with a grain of salt. And because we had no experimental data, there's a lower chance of error. So in conclusion, we were able to meet all of the lab objectives, and we compared the performance between the different things.